So one of the things that we're going to do now is we're going to look at how the ideal gas law equation works, and we're going to use it to explain something that we've been using as a conversion for a long time. So for a long time, we have said that 1 mole of gas occupies 22.4 liters of volume at STP. And so remember that STP stands for standard temperature and pressure. And so what we're going to do is we're going to say, all right, well, why is that true? And the ideal gas law is the reason why that's true. When we talk about ideal gas laws, we're actually looking at the pressure, the volume, and the temperature. And so that's where we get that standard temperature and pressure playing a role. And so we're going to solve this equation. We're going to get to practice using the gas law in that, and then we're going to prove this conversion that we've been using. So our question says, how many liters of space does 1 mole of gas occupy at 1 atm and 0 degrees Celsius? So we're just going to start by writing down our equation. PV equals nRT, and then I like to make a list. So P, V, N, R, and T. And I'm going to go through my equation, and I'm going to fill in the info that I have. So for my pressure, I know that my pressure has to be in ATMs, and so I see that I have 1 ATM of pressure. And for my volume, that's going to be in liters, and I'm looking for that. How many liters of space? So that's going to be my variable, or my X. N is the number of moles, and so I can see that I have 1.00 moles of gas. R is my gas law constant, so I'm always going to use this number, 0.0821 L ATM MOA LK. I like to say latamolk. So that's going to be my gas law constant. I'll always use that number for R. And then T, my temperature. My temperature is in 0 degrees Celsius, but I know that has to go to Kelvin. So I add 273 and I get 273 Kelvin. So I'll put that here. 3 Kelvin. Okay, so I am looking for the volume. Well, I have to know how to rearrange this equation to solve for volume. So I know that since it's pressure times volume, if I divide both sides by the pressure, now I've rewritten my equation so that V equals N times R times T over P. And so I'm solving for the variable that I'm looking for. Okay, so what I'm going to do is I'm going to take my info and plug it in. So for N, I'm going to say 1.00 moles times R, which was 0.0821 L ATM MOL K, times T, my temperature, which was 273 Kelvin, and I'm going to divide that by P, or pressure, which was 1.0 ATMs. Now before I even do the math, I want to show you why that variable was so important, or I'm sorry, that unit was so important. So the ATMs are going to be able to cancel, the moles will cancel, and Kelvin will cancel, leaving me with liters. Well, liters is the perfect unit for volume, so I know that I've done that correctly. So what I'm going to do is grab my calculator, and I'm going to just plug that in. So 1.0 times 0.0821 times 273 divided by 1 gives me 22.4133. Equals 22.4133 liters, and we're going to pretend that this is like perfectly 0 degrees Celsius, so I'm going to go with 2 sig figs, so I would say 22 liters. Well, if we look at this, if you remember, STP is 0 degrees Celsius and 1 ATM, and that happens to be what I had, 1 ATM and 0 degrees Celsius, and I got 22.4 liters out of that, which is what we said that the conversion would be. So this proves that if the pressure is at STP, or 1 ATM and 0 degrees Celsius, they're going to 1 mole of gas will occupy 22.4 liters in an ideal world. Okay, and so I just want to kind of refresh what we did, but we went through the problem, we figured out what we were looking for, we plugged in all of our information, we rearranged our equations so that we were solving for volume, plugged in our numbers, took care of our units, rounded for sig figs, and we got 22 liters, which proved what we thought it should be. Okay, so now we're going to look at stoichiometry with this, because since we're dealing with moles, we can use stoichiometry and stoichiometric equations. So far we've covered the difference between real and ideal gases. We know what the ideal gas law states, and we know what each of those units are. and we know about the gas law constant, so I'm going to highlight this so that it sticks out to us. We know how to convert between moles and liters. So we have what is the mole to liter conversion based on the ideal gas law. We know that it's 1 mole equals 22.4 liters, but now we've been able to prove that as long as the conditions are standard at 1 atm and 0 degrees Celsius. If those conditions change, then that volume changes. And so that's what we're going to see in just a second with our stoichiometry. So that's going to answer our last question. How do you apply the ideal gas law to stoichiometry? Okay, we're still on page 100, but I've run out of room. So now let's look at the ideal gas law with stoichiometry. I'm just going to write our equation at the top here because I want us to have it handy. So we know that R is 0.0821 latam molk. Okay, so whenever we're dealing with ideal gas law and stoichiometry, that's going to be when you're converting between compounds, but we're doing this at non-STP conditions. And that's important for us to understand, is that if it ever says something other than 0 degrees Celsius and 1 atm, then we're going to have to use the ideal gas law. So if you start with a liter that is not at STP conditions, then we're going to use the ideal gas law first to get moles, then we'll do stoichiometry. If you are ending with a liter, but it's not at STP conditions, then you're going to use stoichiometry to get the mole, then use the ideal gas law to get to the liter that you want. So let's look at this problem. It says, given the reaction H2 plus O2 yields H2O, if I react 34.5 liters of oxygen gas at 25 degrees Celsius and 1.45 atms, how many grams of water will be produced? Well, I can see automatically that I have liters, but I'm not at 0 degrees Celsius and 1 atm. So I'm going to have to do something with that. Before I do anything, I'm going to balance my equation because I know this is stoichiometry. So I have 2 H's, 2 H's, 2 O's, 1 O. So I'm going to put a 2 here, which gives me 2 oxygens, but now I also have 4 hydrogens. So 2, 1, 2 are my coefficients there. Okay, so I'm going to be taking 34.5 liters of oxygen gas, and I want to end with grams of water. Well, I am starting with a non-STP liter. So that means I'm going to use the ideal gas law first and turn this liter into moles. Then I can do stoichiometry. Okay, so I'm going to just be dealing with this 35 liters. So I've got P, V, N, R, T. Okay. And remember, because I was starting with the liters that was not at STP, I have to do the ideal gas law first to get to the mole, then stoichiometry. So I know I'm getting to the mole, so I'm going to go ahead and put my question mark here. It's going to be N, the number of moles is going to be my variable. So the pressure is 1.45 atms. The volume is 34.5 liters. My R is my constant, so it's going to be 0.021 latam molk. And then my T, or temperature, is 25 degrees Celsius plus 273 gives me 298 Kelvin, because remember that's got to be in Kelvin. Okay, so I'm going to rearrange my equation. So I have PV equals nRT, and I know that I am solving for N. So in order to get N by itself, I need to move its partners over to the other side. So N is going to equal PV divided by RT. All right, so let me plug that in. P is 1.45 atms. V is 34.5 liters, divided by R, which is 0.0821 L atm molk, and T is 298. Okay, so I'm going to go through and cross out my units. ATMs, liters, K, leaving me with moles, which is what I wanted. So I'm going to plug this info into my calculator. 1.45 times 34.5 equals, divided by, and I need to make sure that I put the bottom in parentheses, so 0.0821 times 298, and that gives me 2.04 liters. Okay, and so again, we're going to pretend that this is like perfect temperature, so we're going to go with 3 sig figs, 2.04 liters. So that, I'm sorry, 2.04 moles. Sorry, that's where we're at. 2.04 moles. So I'm going to use 2.04 moles when I'm doing my stoichiometry. Okay, so I'm going to now do the stoichiometry part of this. So I know that I have this equation, and I'm starting with 2.04 moles of oxygen, because that's the compound that I had, and I'm just going to do my conversion. So I need to go from moles of oxygen to grams of water. So I'm already in moles, so I'm just going to go straight to my mole to mole ratio. So moles of oxygen, and I'm going to water, so it's going to be moles of water, and my coefficients here are 1 and 2. So 1 mole of oxygen is going to give me 2 moles of water, and now I need to convert the moles of water into grams of water. And so I know that if I take 1.008, which is hydrogen's mass on the periodic table, so if I look right here, I can see hydrogen's mass 1.008 times 2 plus oxygen's mass, which is 15.999, I'm going to get 18.015. So 18.015 grams of H2O. Okay, and so now I'm just going to multiply across and then divide by what's on the bottom. My moles cancel, leaving me with grams of H2O. So I'm going to take 2.04 times 2 times 18.015, and then I divide that by 1 and divide it by 1. And so that gives me 73.5 grams of H2O. So that would be my answer. And so we remember that this was just basic stoichiometry, but I couldn't use 1 mole equals 22.4 liters because it was not at STP. And so since it was at non-STP, that is not true. We had to use the ideal gas law in order to take into account a different pressure and a different temperature than we were used to. And so we plugged that in, plugged in our values, and we got our moles, and then we did our conversion. But since we started with non-STP liters, we had to use the ideal gas law to get to the moles first, then we did stoichiometry to change our compound. Okay, so that pretty much covers the ideal gas law. We have answered all of our questions. We know that ideal gases do not account for, ideal gases do not account for the volume of particles, and they have elastic, bouncy ball collisions with no attractive forces. We know the equation for the ideal gas law is PV equals nRT, pressure in ATMs, volume in liters, N is the number of moles, R is our gas law constant, which uses all of those units in its own derived unit, and temperature is in Kelvin, so we had to add 273. We know how to take the information from a problem, plug it in, rearrange our equation for the missing variable, multiply, divide, and get our answer, and so that's how we proved our conversion of 1 mole equals 22.4 liters at STP, because that was 0 degrees Celsius in 1 ATM. And we also learned how to do ideal gas law with stoichiometry. So if we're starting with liters, and we're not at STP conditions, and so let's just write that down over here on the side. STP is 0 degrees Celsius and 1 ATM. If you are not at those conditions, you're going to have to use the ideal gas law first and turn it into moles, which is what we did, and then you can do stoichiometry, or like you're going to see in some of your homework, if you're wanting to if you're starting with, let's say, grams, but you're wanting to end in liters and your conditions are not perfect, then you're going to do stoichiometry, but instead of going to liters at the end, you would stop at the moles and then plug your mole answer in here and you get your volume. But that's only if you're ending with liters. All right, so what we're going to do now is we are done with our notes for today, but I'm going to start a second video where we're going through some practice problems with you. This was M100 ideal gas law.